Page 53, the twins paradox. This is a classic. This one's fun. All right, this is where we can actually get into the idea of time travel. So here we go. One of a pair of identical twins is selected to be a crew member of a deep space expedition to a star 11 light years distant. The other twin will remain on Earth. The vessel will travel at point 998 C. Discounting the time spent exploring the star system, determine the ages of each twin upon the vessel's return to Earth. Okay, so let's set this one up. So point 998 C, and we've already figured out gamma from the previous example, 0.063. All right, the distance is 11 light years. So a round trip is going to be 22 light years. And I just want to, let's throw a little extra wrinkle. Let's say that the twins celebrate their 21st birthday on the day of the launch. So we have the Earth twin and the space twin. The Earth twin is 21 years old, as is the space twin. So first let's talk about the Earth twin. And we're going to kind of rough this out a little bit. Like I've said before, in astronomy, we round things quite often. Okay, so from the Earth twin's perspective, that spacecraft moving at 0.998 C, that's pretty close to the speed of light. And so if we want to round it, we can just say, yeah, he's moving at pretty much light speed. And if we look at it that way, then we can see that from the Earth twin's perspective, it's going to take that spacecraft 11 years to cover 11 light years, and 11 years to come back, another 11 light years. All right, so it will be 22 years before that vessel returns and he sees his twin brother. He will be 43 years old. All right. But what about the space twin? Well, okay. T delta equals T over gamma. Remember, T is time as experienced by the moving object, and that would be the space twin. Okay. So what does T equal? T equals T delta times gamma. Okay, so that's going to equal T delta, that's time as observed by the stationary observer, that's the Earth twin, that's going to be 22 years times gamma, 0.063. .386. That's roughly 1 year, 5 months. The space twin will experience only 1 year, 5 months of time. When the space twin returns, he will be 22 years, 5 months old. His twin brother will be 43 years old. And no, he doesn't suddenly catch up in time because he has not experienced 22 years of time. He's experienced only 1 year, 5 months of time. Pretty wild, huh? Okay. On page 54, there's a gamma chart for relativistic velocities. And what I want to point out here is if you look at the left-hand column, you'll see velocities that get closer and closer to the speed of light. And on the right-hand column, you see what gamma comes out to. And so we start at 0.9 C, and if you round it to 2 places, gamma is 0.44. 0.99 C, gamma becomes 0.14, and so on. You get all the way down. You see how much smaller gamma gets. In other words, the takeaway here is that the closer you get to C, the smaller gamma becomes. That's the important part. Now let's take a look at page 55. Okay. A crew of astronauts leaves Earth to explore deep space. Given from the crew's perspective, they will experience 1 year of shipboard time traveling to within a billionth of the speed of light. And that gamma, number 2, gamma, for their velocity is 0.00001. Now, let's be clear about this. 1 year of shipboard time. That means that we're going to stock this ship with enough food, water, and toilet paper to last these guys 1 year. So how much time will have elapsed when they return? Well, T delta equals T over gamma. Remember, T is time as experienced by the moving object. 1 year divided by 0.00001. That comes out to 100,000 years. So when they come back, 100,000 years will have passed on planet Earth, and there's no going back. It's a one-way trip. All right, well, let's cut these guys a break. We'll send them out for only 1 day. That means when they come back, 100,000 days will have passed. Well, what's 100,000 days? Well, 100 divided by 365. Now I'm going to round that. That comes out to 274 years. So they go out for 1 day at that speed, and when they come back, 274 years will have passed. Everybody they know will be gone. Wow. And there's no escaping this. This is how the universe works. It really is. I have a little point to ponder at the bottom of the page for you to do. Okay, let's pause here, and then we're going to talk about some other practical problems of approaching the speed of light.